complex ion equilibria. Remember what a Lewis acid is? Electron acceptor. So, Bronsted-Lowry acids and bases talked about proton acceptors and donors, and the Lewis acids and bases talk about the electrons. So Lewis acid is an electron acceptor. Transition metal ions are often good Lewis acids, and water molecules can act as Lewis bases, electron donors. Because if we look at the Lewis dot structure for water, the water has 2 lone pairs of electrons. Well, that didn't turn out very well. It can donate those electron pairs to a Lewis acid. So if we look at silver in solution, silver ions are actually hydrated in solution. The silver ion is going to have 2 water molecules with it. We've got a Lewis acid, Lewis base thing going on. You don't actually have bare silver ions floating around in water. And this is called a complex ion. Complex ions have a central metal ion bound to 1 or more ligands. And the ligand can be a neutral molecule like water, or it can be an ion. But these ligands act as Lewis bases and interact with that central metal ion. So AgH2O2 plus is a complex ion where silver ion is the central metal ion and water is the ligand. So yeah, they kind of hook up, they hang out. If we add a stronger Lewis base, it's going to displace the water in the complex ion. So here's silver complexed with water. If we throw ammonia in there, ammonia is a stronger Lewis base than water is. And you could figure that out by looking at their KBs. And so the ammonia is going to displace the water and we'll end up with AgNO32 plus, and the water got displaced. So like we often do with hydronium ion, we leave the water out. And we understand that it's there, but we just leave it out. And so for simplicity, we'll just write Ag plus 2NH3, forming this complex ion. So to me, that is similar to what we talk about with the hydronium ion. So you got H2O plus H2O, forming H3O plus OH minus, right? Well, if you remove a water molecule from each side, if you leave water out, you end up with H2O is in equilibrium with H plus OH minus. It's shorter, it's simpler. We just understand that the water is hydrating that hydrogen ion, just like the water is hydrating silver ion in solution. Well, here's an equilibrium, and it's going to have an equilibrium constant. So here it's called Kf, the formation constant. So it's the constant for the formation of that ion. You have to have your reaction in the correct direction, right? You wouldn't want to put the complex ion coming apart into the individual ions. So formation helps me to remember. It's the equilibrium constant for forming this. And that is going to be the same type of equilibrium expression that we've looked at before. The products divided by the reactants raised to the power of their coefficient. There's a table, formation constants, for a bunch of different things in water at 25 degrees Celsius. So here's a problem, complex ion equilibrium. You mix a 125 ml sample of a solution that's 0.0117, that's a familiar number, molar, in nickel chloride with a 175 milliliter sample of a solution that is 0.250 molar in ammonia, After the solution reaches equilibrium, what concentration of nickel remains? Formation constant is given, 2 times 10 to the 8th. Well, let's write this out. Yeah, that didn't work so well. Nickel, 2 plus how many ammonias? This is the ion that it forms. This is the complex ion. There's 6 of them.
Yeah.
Now, how would you know that? Well, when you went to look in the table to find the formation constant, it shows you this, and there's no other options, and so, oh, well, that must be what it does. Some of these things are just not, there's no great reason behind them. So that's this guy. Okay? And we've got KF for that. So we've got information to find out what the concentration of nickel and ammonia are. We can't just use 0.0117 and 0.250 though, can we? Because we had 125 milliliters of this mixed with 175 milliliters of that. So there was some dilution going on, right? So we're going to have to calculate those. And I'm just going to do one of them up here at the top. So 0.125 liters of 0.117 moles per liter gives us the number of moles, right? And what's the total volume? It's 300 milliliters. So I'm going to get this 0.125 times 0.117 is going to give me 0.0146. And then I have to divide that by 0.3 liters.
Yeah, that'll change it. Okay.
Yes?
There is 0 in front of the 0.1.
Well, that's good, yeah. That does change things just a wee bit.
Yeah.
But, you know, when I tell my students, oh, well, yeah, but it's wrong, like, but I just forgot the 0.
Here's off by...
Yeah, well, you just killed a patient,
Yeah.
right?
Yeah. Order of magnitude.
It's just 1 order of magnitude. Well, let me just adjust your salary by 1 order of magnitude.
No.
No, thank you. Nobody wants that. See, I know the things that people are touchy about. Oh, I'll just adjust your weight by a factor of 10.
Which way?
It's going to be bad either way, right?
Yeah.
You might be really overweight. You weigh, 400 pounds. Now you weigh 40 pounds. That's not going to be good. Okay. So that would be the nickel. So that's what I'm doing here, and I'm getting 0.004875 is the concentration of nickel. And for the concentration of ammonia, I'm doing the same thing, but I've got 0.175 times the concentration of the ammonia times 0.25, and I'm going to divide that by the total volume, 0.3, and I get 0.1458. 3's forever. Did I do that right?
It feels right.
It feels right. I feel really good about it, so it must be right. And we're starting out here with none of that, right? Look at that formation constant. Big or little? Big.
Oh, negative.
That was supposed to be an easy question. It's big. 10 to the 8th. what does that tell us about the direction that this reaction is going to go? It's going to go heavily to the right. So we're going to be best off saying, well, let's push it all the way to the right and then calculate x coming back. So I'm going to take the smaller number, and that's going to come out to be essentially 0, and I'm going to subtract that from this guy as well. There, I've got that number in there, so I'll just subtract 0.004875. So I'm getting, oh yeah, I divided, that didn't work. 14583. 3's forever, minus 0.004875. That's better. 0.14096 or so. If we're we should probably do some semblance of keeping track of sig figs, right? And then this is going to be plus 0.004875. That's what we want to use for our starting initial concentrations. And then we're going to say, well, it's going to go backwards a smidge, right? We have to come up with a number for this. So this is going to be, I did something wrong.
What?
6.
Didn't do this, huh?
There's a 6 in there, right? So this is fine, but I'm going to lose 6 of these. So this is where you could also go astray. You could multiply or divide, and you have to decide which is which. So I'm just going to be safe here. So this is the molarity of the nickel. And I want to find out the molarity of the ammonia that would go away because of that. 6 moles per liter of ammonia for every 1 mole per liter of nickel. So I need to multiply by 6. I take this guy times 6. So that's not right. 0.14583. What's really dumb is I made the same mistake this afternoon. Okay, so now I'm getting 0.11658.
Would that work if you think of 0.04875 as x, and then you just go minus 6x?
Yes.
6 times that.
And that probably would have been better. So if I said this is minus x, then this is minus 6x. This is plus 1x, right? And then you say, well, all of this is going to go away, and you'd come up with where we are now. That's safer. Mm-hmm. So I don't know, maybe this is just really crappy teaching, but this is thinking it out. This is how people solve real problems. Especially when you get to this level of chemistry, it's not just a set number of tricks that you need to learn how to do, right? Because there's going to be one on the test that you've never seen before. And can you think about it? So I'm demonstrating how to think about it, which, for whatever, anyway. It's the process, yes. So we're going to say, okay, if it went all the way to the right, this is what we've got for this guy, and this one's 0. But we know that that's not going to be 0. It's going to be really small, but it's not going to be 0. So now we're going to say it's going to come back the other way. This is going to be minus x, and this is going to be plus 6x. and that's going to be plus X. And so we've got very messy numbers here. 2 times 10 to the 8th is going to equal the concentration of this at equilibrium, which is this number minus X, 0.004875 minus X, divided by the nickel, which is just X, times this guy, 0.11658 plus 6X. And what happens to that one? It's raised to the 6th power. You could use the solver. Do you think X is going to be small relative to 0.004875?
Yes.
Probably. So let's try using the X is small approximation, and then if that doesn't work, we can do it the other way. So X is small says we're going to take off that guy and we're going to take this guy off, because we're saying X is small enough that if we're adding or subtracting them to some other number, it doesn't really matter. And so here we need to take the 6th root of something. So the 6th root arguing with my calculator. There we go. The 6th root of 2 times 10 to the 8th times oh wait, I'm doing it upside down. Okay, this one is messy. Let's not be doing this in our heads. Yeah, this is one where you could easily end up solving for 1 over something. So X equals, yeah, because it's not, we don't have to do the 6th root. See, I'm just so screwed up today. 0.004875 divided by 2.0 times 10 to the 8th times 0.11 658 to the 6th power. It's always better to write it out before you stick it in your calculator. 0.004875 divided by 2 times 10 to the 8th divided by 0.11658 to the 6th power. X equals 9.7 times 10 to the minus 6. That'd be more. The book comes up with 9.6 times 10 to the minus 6. Yeah, so that bothered me, and so I tried using all the digits. I tried rounding. I don't know how they did it. Any questions? What a mess. So complex ions can affect the solubility of ionic compounds. So here's a statement in bold. That must be important. The solubility of an ionic compound containing a metal cation that forms complex ions will increase the presence of Lewis bases that complex with the ion. So I don't know about you, but that doesn't make a whole lot of sense to me. The most common Lewis bases that increase solubility are ammonia, cyanide, and hydroxide. But let's look at this little equation here. Ammonia plus silver chloride forming this complex ion of silver with chloride. When you add ammonia, it complexes the ion, and you don't have as much silver that can precipitate. So it's basically kind of trapping it. And so that will cause the solubility of this compound to increase. You can look at it this way. So here's KSP for silver chloride. Silver chloride, when it dissolves, we get silver ion and chloride ion. Here's the formation of the complex ion. Silver ion plus 2 ammonia molecules forms the complex ion. Here's K formation, big number. If we add these two chemical equations, we see that the silver ions cancel out, they get used up, right? Silver ions formed by silver chloride dissolving react with the ammonia molecules to form complex ions. So this is the net reaction down here. If we're adding equations, what do we do with the equilibrium constants? We multiply them. So for this equation, chemical equation, K will equal KSP times KF, which is 1.1, which is wrong. I copied and pasted. You've got the book. Look it up.
Appendix.
No, it's in the textbook.
Oh, good.
And there magically we have fixed it. I'm going to cross these out again. So equilibrium constant for this reaction is KSP times KF, 3 times 10 to the minus third. Now, that's still kind of a small number, but it increased by a factor of 17 million. We've been looking at all these, 10 to the minus 3, 10 to the minus 10, blah, blah, blah. That's a huge difference, right? So this equilibrium constant is much larger, 17 million times larger than the KSP for silver chloride in pure water. That makes the relatively insoluble silver chloride become quite soluble if there's ammonia present. Now, this thought occurred to me. It's just, it's one of those things where you go through life and you never really think about it, and then all of a sudden it dawns on you. Why do people use ammonia when they clean? House cleaning. A lot of things have ammonia in them. Well, ammonia forms complex ions. It increases solubility of insoluble compounds. Oh. It's good for all kinds of scummy things, yes. And this isn't the only reason, but this is one reason why I think ammonia is a good cleaner. Stinks really bad, though.
Makes everything else smell good in comparison.
Yeah, it makes everything smell good in comparison. Well, maybe the bathroom didn't smell so bad before you cleaned it. Okay, amphoteric metal hydroxides. These are crazy things. So we learned back in section 5 of this chapter that many metal hydroxides are insoluble or very slightly soluble in pH neutral solutions, but that metal hydroxides are more soluble in acidic solutions. Do you remember why? Well, let's look at, let's do calcium hydroxide. So when calcium hydroxide dissolves, it's an equilibrium, you get calcium ion and hydroxide ion. Now, if you put acid in there, what does it do to the hydroxide ion concentration? It decreases it. What does that do to the equilibrium? Shifts it towards the products. Okay? So metal hydroxides are more soluble in acidic solutions. Vinegar's an acid. Vinegar is often used in cleaning. Yeah, it has cleaning on the brain. What's cool, though, is some metal hydroxides are amphoteric. They can also act as acids. I know, right? How is that possible? How could a metal hydroxide act as an acid? Well, it's the whole complex ion business. So here we have aluminum hydroxide. That can react with hydroxide ion and form a complex ion. The aluminum hydroxide is going to be soluble at high and low pH, but insoluble in the middle. What? What kind of craziness is this? Well, let's look at it in more detail. Yeah. I know you wanted to know. So, aluminum ion in solution is inherently acidic. I'd like to say basically acidic, but that wouldn't work out very well. Basically acidic. Aluminum ion is hydrated, right? It forms a complex ion with water. You can look up the Ka formation for that. It's big, right? So here we have hydrated aluminum ion. When that encounters a water molecule, it can remove protons from the water molecule. So now we're going to get Al H2O5 OH, and now the charge is one less because we've got a hydroxide ion here. And so here we've got the hydronium ion. When we add base, it drives this to the right. So this is acting as an acid. It's generating hydronium ions in solution. When we add base, that's going to cause this reaction to go further this way because we're using up the acid that was formed. So we add base, and we'll get another OH on that aluminum, and if we add more base, we're going to get more, and so we end up with this complex. This is insoluble. This is essentially AlOH3. It's not soluble in water. So this was soluble. We added more and more base until we got to this neutral point, and now this is not soluble. But if we add if we add base, if we add more base, it's going to dissolve the solid because you're going to form an ion again. You kind of have to look through that before you really see what's going on there. How would I make a test question? I don't know. I tend to avoid making test questions. I pick them out of the test bank. Sometimes I switch them a little bit or mess with them, but why be creative if you don't have to be? So this is the one that's insoluble. What's different between this one and these other guys that are soluble? Has a charge. This doesn't have a charge. This has a charge. That one has a charge. This one has a charge. So here's the aluminum complex ion in acidic solution. As you add base, you'll see precipitate form, and as you add more base, it'll dissolve again. Craziness.
Oh,
Really crazy. Cations that form amphoteric hydroxides, not all of them do, are aluminum, chromium 3, zinc, lead 2, and tin 2. And the extent to which it will dissolve both in an acid and a base depends on how amphoteric it is. And